This lesson we're going to be talking about something called the addition rule and conditional probability. So first, a couple of definitions. Mutually exclusive events are events that cannot occur at the same time. So two things that it's impossible to be doing both of them at the same time. Like you can't have an event of you're in English class and an event of you're in math class occur at the same time. You can't have both of those classes at the same time. An inclusive event is events that they don't necessarily have to, but they can occur at the same time. So you could be having a donut and you could be eating it inside, but that doesn't mean that you have to eat it inside. So the event eating a donut and the event being outside, they're inclusive because they could happen at the same time. What's called the addition rule is it's when two events A and B are mutually exclusive, so they cannot happen at the same time, the probability that A or B will occur is the sum of the probability of each event. When two events are not mutually exclusive, there is an overlap, and so there's an intersection. Okay, so that's going to be different. A conditional probability is the probability of one event given that the other one has already occurred, and I mentioned that in the last lesson. But if you have probability of A given B, it means you already know that this happened, so however that affects A happening, that's going to have some bearing on the outcome. The next thing is a union of events. We talked about that last time. The union is that where events potentially happen together, like you can have milk or a cookie, or you can have both, but you don't have to have them both. If you have milk and a cookie, that's an intersection, and that means you have to have both of them. So a union is simply that you could have one or both of them. Okay, I've got a couple things here on the screen. This box that I have over here on the right, this is a summary of the different rules that we have. And so we talked about this in the last lesson right there with independent events, because mostly we've been talking about independent events so far. Something that's not independent is if you're pulling something out of a bag and you replace it, then that would make it independent. But if you don't replace it, then that's going to make it dependent. So that's like the first assignment that we had. The next thing that I have over here on the left is I have a deck of cards. And so if you're not familiar with a standard deck of cards, this is what it looks like. You have 52 cards altogether. There's 4 different suits is what they're called. There's hearts, diamonds, clubs, and spades. Each suit is numbered 2 through 10, and then you have face cards, jack, queen, and king. Ace is a special card. It could actually count for a couple different things depending on what game you're playing. We will not be counting that as a face card. Okay, so an ace is not going to be counted as a face card. So when I ask you about a face card, I'm only now asking you about jack, queen, and king. Let's go ahead and we're going to do some problems with the cards today, and I'll kind of explain a little bit more as we go. We're not going to be talking about jokers at all. And the ace is also the highest card. So that's going to be the highest card that you can have. Okay, so let's talk about some different events. So the first is deciding if events are mutually exclusive or inclusive. And so you need to think about, can they happen at the same time? So can you roll an odd number and roll a 2 at the same time with one die? So can you roll a 2 and it's an odd number? And obviously that cannot happen together because 2 is not an odd number. So this one is going to be mutually exclusive. And no, you can't abbreviate that. Okay, the next thing is, can you wear jeans and wear tennis shoes? So you can wear jeans, you can wear tennis shoes. Could you do that at the same time? And that answer is yes, obviously you can. So that's going to be inclusive. Okay, now thinking about a deck of cards, could you draw a club and a black card? So can you draw a card that is both a club and it's black? And that is obviously going to be inclusive because clubs are black. So you could choose a card that is a club and black. We could say it the other way around. Can you choose a black card that is also a club? That's also inclusive, even though not every black card is a club. And then the last one, I'm drawing a 4 and a face card. So if you pull one card out of the deck, can it be a 4 and also a face card? And obviously that cannot happen because a 4 is not a face card. And so it's not possible to have that at the same time. Another example of mutually exclusive would be if you roll a 5 and a prime. So could you roll the dice and get a number that is both 5 and prime? And yes, you could. What if I said 5 and odd? Yes, you could. That doesn't mean that every odd is 5. So what if I said, what if you roll an odd number and a 5? So you could do both of those at the same time. Okay, the probability of the following events. I'm going to give you some information about these different clubs. Okay, and so some numbers to fill in your diagram. So looking at this diagram with these numbers, what is the probability that if you choose a student at random, they are in at least 2 after-school clubs? Well, the first thing I have to do is figure out how many students are we talking about. So if you add them all up, there are 60 students. So I could choose any one of 60 students. Okay, what's the probability that they're in at least 2 after-school clubs? So I can do this a couple ways. I can say, well, these guys are in 2 after-school clubs. So are they, so are they, so are they. The one that's in the middle there, they're in at least 2 after-school clubs. So I just need to count those students. So I could say 7 plus 8 is 15, plus 11 is 26, plus 10 is 36. So the probability is 36 out of 60. And you can simplify the fraction. And you can write it as a decimal as well. I'll be telling you that you can write a lot of things as decimals here. All right, the probability of being in all 3 clubs. Well, how many students are in all 3 clubs? That's only 8 of them out of the 60. And so that's going to reduce to 2/15. And depending on what the directions say, you may or may not turn that into a decimal. If you are turning it into a decimal, make sure you do not round it unless you're told to, and round it the way that you're told to do it. Okay, for the next set of questions, we're going to consider a standard deck of cards. So you can look back at the picture on your notes if you need to. Remember, the aces are not face cards, and also aces are the highest cards. So that means that aces are not less than 2. Okay, so they're not a 1. Now, of course, depending on the game you play, they might be a 1, but we're not going to consider it that way. So what's the probability that you get a card, and it's a face card or it's a 3? So you can look back at your picture. How many face cards do I have? There's 12 of them. How many cards do I have that are 3s? There's 4 of them. Are any of those cards both a face card and a 3? Because if so, I'd have to take out the duplicates. And the answer to that is no. So there are 16 cards that are what I want to pull out of the 52. And so that's my probability. So basically you're doing 12 out of 52 plus 4 out of 52. And that's 16 out of 52, which is 4/13. We're just going to leave that as a fraction because it doesn't turn into a great decimal anyway. Okay, the next one, number 8, the probability of getting a 5 or a black card. So the probability of getting a 5 is 4 out of 52. The probability of getting a black card is 1/2. It would actually be better in this case if I left my denominator as a 52. It'll just make the adding easier. Are there any cards that are both 5 and black? Because if they are, we've already counted them as one or the other, so we cannot count them twice. There are 2 cards that are black 5s. So I'm going to take out the 2 that I already counted in both this set and this set. I can only count them one time, so I'm going to take out one of those sets. So what I've got is about 4 plus 26 minus 2. That's 28 out of 52. So 28 out of 52. And that reduces to 7/13. And I'm just going to leave it like that. Okay, pause the video and see if you can do 9 and 10. And you can look back at your pictures and see if you can get that right, and then come back and see if you did it right. Okay, the probability of getting a club or a red. So the probability of getting a club is 1/4 or 13 out of 52. It's probably better to leave your denominators big instead of reduce your fractions here, because you're going to have a lot of fractions to add, and if they all have common denominators, you want to keep it that way. Okay, the probability of getting a red card is 1/2 or 26 out of 52. And then are there any cards that are both clubs and red? And the answer to that is no. So those are mutually exclusive events. And so if you look back on the page where I had this right here, that's describing what we're doing. If you have mutually exclusive events, then the probability of getting both of them is just simply add them together. So 13 plus 26 is 39. So 39 out of 52, that actually does not reduce, and so we'll just leave it like that. The probability of getting a face card is 12 out of 52. The probability of getting a spade is 13 out of 52. Are there any face cards that are also spades? So if you go back and look at your picture, you've actually got a few face cards that are also spades. There's 3 of them. So we're going to take away 3 of them because we've already counted the jack of spades, queen of spades, and king of spades right there when we counted the face cards. So we don't want to count them again when we did the spades. So we're going to just take them out. And so we're going to have 12 plus 13 is 25 minus 3 is 22 over 52. And that reduces to 11 over 26, and that doesn't reduce anymore, and the fraction's not that great. So we're just going to leave it. Sorry, the decimal's not that great. And remember, when you're doing these cards, we're not ever counting jokers. They're not counting at all. Okay, the last section, we're going to consider a survey. 100 people were asked if they favor, oppose, or have no opinion on an upcoming bill before the legislature. So is it possible to both favor and oppose the exact same thing? The answer to that is no. So these are mutually exclusive events. So if we look at the table, we've got, out of the 100 people that were asked, we have those in favor were 18 men, 9 women, for a total of 27 out of the 100. Those that were opposed would be the 12 men, 25 women, 37 total. And then those that had no opinion were the 20, the 16, and the 36. So you see that every way, like we add up to 50 men, 50 women, 100 people total, and all of the numbers add both ways. So what's the probability that you choose one of these 100 people at random and you get somebody that either opposes it or has no opinion? So the people that oppose it are 37, and those that have no opinion are 36. So 37 out of 100 plus 36 out of 100, those are all the people that oppose it. And again, we've already established you can't both oppose it and have no opinion. So that's going to be a total of 73 out of 100. You could write 0.73 depending on the directions, of course. Probably not put the 73%. Usually let's just keep it as a decimal unless we're told to do something else. Number 12, it says, is number 11 mutually exclusive or inclusive? So we've already said you can't be opposed and have no opinion at the same time. So these are mutually exclusive. Okay, what's the probability that you choose a man or you choose someone that opposes? So what's the probability that you choose a man? So 50 out of 100 were men. What's the probability that you choose somebody that opposed? So that's 37 out of 100. What's the probability that you chose a man that opposes? And there are 12 of them. So we already counted those 12 in the men. We can't count them again for the opposition. So we're going to take out the 12 out of 100 because we're not counting them twice. And so that's going to give us 50 plus 37 is 87 minus 12 is 75 over 100. So that's 3/4 or 0.75. And remember that that's the man who opposes. Man opposing. Okay, and then the last question is number 13, mutually exclusive or inclusive. And so in other words, can the man be opposing and the man? And they can be, so that is inclusive. And then the last question, why do you think we like to use decimals instead of fractions and probability? A lot of times when we're using fractions, if you look at some of the fractions that we have, like 73 over 100, 75 over 100, but then we have 26 over 52, 4 over 13. And so if you're telling like which one is the better probability, like which one of those is a better probability, it's a lot easier to compare fractions if they have the same denominator, but since so many of our fractions don't, that's really why decimals are easier, because you can compare them easier to tell which one has a greater probability. And that's why we would want to use decimals a lot of times when we're dealing with probability.